Hi, happy to be here today. There's some great content that I'm going to share with you that really will be pretty cool to take a look at. And let's go ahead and get started with a screen share here. So I'm going to share my screen. Let me just talk through a little bit this notebook if you're not familiar with it. So I actually got this from GitHub for the link that I shared earlier. And there's a bunch of different notebooks in here that you can explore on your own afterwards. But inside of this repo here, I'm actually going to be reviewing 4 different notebooks, or I'm going to be reviewing 1 of 4 notebooks. But you can click on any of these links. So in this case, there's day 1, part 1, day 1, part 2, day 2, part 1. I'm going to be clicking on this one. But if you click on it, it'll actually open up something called Colab. And for data science, really the predominant platform now is Jupyter Notebooks. And Google has a new platform called Colab, which is a hosted version of Jupyter Notebooks. And so that's what I'm going to be using for this presentation. And what's really great about it is that you can actually execute line by line every single thing I'm doing. So I'm not showing you something that you can't repeat. There's nothing to install. It's completely set up for you. So it's really a dream environment for doing data science. So let's go ahead and start at this beginning of this notebook here. What we're going to talk about is some of the things that happen in a data science project around I/O. And in particular, when you do data science, you need to get the data from somewhere. And this often becomes a really difficult problem as how do I actually get data into my system and deal with it. And in this section here, which I don't have time to fully go over, there's some links here that show you how to write a file in Python. And I can show you really quick here. It's just a few lines of code. I can say with open, create a file, and then write a line out. So it's just a couple lines of code. And also reading a file, the same thing. But these are really important fundamental operations that you have to do in Python when you're doing data science. And they're really straightforward. And I have a whole series of things for you to take a look at. Likewise, there's some instructions here on how to use pandas as well. Also how to use concurrency in Python. There's a lot of really interesting problems in Python with concurrency. I'll let you cover those on your own. What we'll get into is right into really the meat of data science. And we're going to walk through from the beginning to an end how to do data science with Python. And we're going to cover the MBA, which is, I think, a good topic for this kind of a webinar because most people have at least seen an NBA game, or maybe you're a really hardcore NBA fan. So this project in particular, one of the things that I did when I started it was I didn't really even know what I was trying to do. And a lot of times with data science, you don't know what you're trying to solve. It's like being a musician where maybe you're hanging out with the people in your band and you're playing the guitar and you're playing the piano and you kind of try things out, and then you figure out that actually you're going to write some song together, but it's all through this really improvisational aspect of creating music. Data science is the same way. A lot of times you may have an idea or you may try something out, but ultimately you end up in a different direction, and that's completely fine. So in this case, I was very curious because I'd worked at a social network for sports for several years about what I could do to investigate why teams were worth what they were. Like, why is the LA Lakers worth so much money when they were really a very bad team for the last decade? And then why was maybe a team like the Houston Rockets not worth as much? And so what I did was I had to collect data from the arena attendance. So that was a difficult problem. I found it on a Forbes website. I just cut and paste it, put into a file. Next, I grabbed some data from Wikipedia. What was interesting about Wikipedia is that it's a proxy for global popularity. And so it's a great open source data set that you can grab information on. You don't have to have an API key. You can just go ahead and grab it. I also looked at Twitter, and I found some really interesting things that we'll cover in a second. And in fact, Twitter and Wikipedia, later I discovered, became a very important way to predict who's going to be successful in the NBA. And then I grabbed census data. So I looked at population density, real estate values. I looked at endorsements, salary. And then I looked at, you would think this would be the first thing I would look at, but I then finally looked at the NBA data set performance. So in order to do comprehensive data science here, you can see I had to find and hunt down 1, 2, 3, 4, 5, 6, 7 different data sets. And this is typical of a data science project. So there's a couple links here. If you want to explore on your own how to actually grab data from Twitter, you can look at this link. If you want to see how to grab data from Wikipedia, you can grab this link. But let's go ahead and assume that we collected all that data, and now let's start processing it. So the first step in a data science project is I typically have a big stanza of imports. And so this is really common. If you go to Kaggle, you'll see a similar style. I run this, and then this will go ahead and do those imports. Now, I said earlier that Colab is a really powerful environment for developing. And part of it is that it's a hosted environment where I don't have to install all the Python packages. And let me just show you really quick. If I go to runtime here and I go to change runtime type, you can see I can actually target a GPU as well. So that's another secret advantage of Colab is I can do GPU-based deep learning. And also Python 3, I can toggle it if I wanted to and go to Python 2. So that's why this is so easy to do these imports. Next, I'll go ahead and grab that data. And this is another secret trick here is that if you want to store repeatable information for a presentation, you can actually check small files into GitHub and then reference them inside of pandas. And you can see here that I do pd.readcsv. This allows me to make a data frame that grabs that data directly from GitHub. So here we have the Chicago Bulls, Dallas Mavericks. We have how many games they played, what the attendance percentage was. So in this case, you can see the Chicago Bulls had actually incredibly high attendance, more than even capacity. And then this is the total attendance for the year. Almost 1 million people attended the Chicago Bulls games. And then this was the average attendance. Next, I want to grab a different data set. So I go here and I grab endorsement data. And we can see, this is from a couple years ago, LeBron James was one of the most endorsed players in the NBA. He made $55 million. So he makes more in endorsement than he does actually in salary. And then I look at the valuations of the teams. And again, I grab this from Forbes. I just cut and paste it, put it into a file, and then checked it in. So a lot of times you don't necessarily need to programmatically access the data. You can just cut and paste it and put it into a repo. Then I grab the salary. And from here, again, we had that earlier. I look at some player impact performance scores. So these are official stats from the NBA. And then I go into the plus minus, which is a stat that's an interesting stat that shows how effective a player is when they're on or off the court. And it's no surprise that LeBron James is actually one of the most effective players in the NBA, and he contributes 20 wins just by being on the court. And so that's why teams were so interested in having him come to their team, is that he instantly gives their team an additional 20 wins. Again, I grabbed some more stats here just so I have a lot of reference here. And then finally, I grabbed my final stat here before I do my initial analysis. And this is a stat called ELO. And ELO is pretty interesting in that it is a strength of schedule metric. And so what this does is it shows how good you are relative to other teams. And so later we'll get into why that's going to be really important for our analysis. And you can see from a couple of years ago that the Golden State Warriors were actually the highest rated ELO. Now I can get into a phase called exploratory data analysis. And it's worth pointing out that in a data science project, there's typically 4 different components to a data science project. There's the ingestion phase, which is what I just did. I went through, I collected the data, and that actually could take 80% of the time, believe it or not. Then there's the exploratory data analysis phase. And the exploratory data analysis phase is a lot like, if you're going to buy a house, you may want to go around, kick the doors a little bit, look at the sink, turn on the water, flush the toilet, make sure that works, look at the backyard, make sure it's proper drainage. It's kind of the same concept as you go in there and you look at what you've got, what you've collected, and you make sure that your assumptions are correct. And so that's phase 2. Phase 3, which we'll also get into, is modeling. And that's where you go ahead and you create a predictive model. And then stage 4 is conclusion. So we're going to go through all those phases. I just went through ingestion. Now we're on exploratory data analysis. So one of the things I can do here is I can start merging this data together. So I had multiple data frames, multiple data sources. So I'm going to run this code, And what this does, if you see this merge operation, is it takes the team in two different data sets, the attendance data set and the valuation data set, and it squishes them together. Now, if I do a head operation, you can see that actually now I've got an additional column. So I can just keep doing this to collectively add things together. Now, another thing I can do in this exploratory data analysis phase, this investigative phase, is I can run a correlation. And this is important for machine learning because one of the things you look at with machine learning is the signal. So why does one column relate to another column? And this can help you decide what features to put into your machine learning model. And so from here, we can see that, for example, let's see, the valuation of the teams is highly correlated with the total attendance in millions. I mean, not like massively correlated, it's more like an average correlation, but it's, in this case, there's a 53% correlation. So that's not surprising. You would expect that what a team is worth and how many people attend would be somewhat related. Another thing you can do is you can do a correlation heat map. And a correlation heat map is a visual way of looking at that same data. So in this case, if we go through and we look at, again, the evaluation here, you can see that the more orange it is, or the more, the lighter it gets, the more highly correlated it is. In this case, this is just showing that the same thing is correlated against itself. So that's why you see like a 1 here. But again, if I look at the valuation right here, and I look at, let's see, if I look at the valuation and I look at the total attendance in millions, you can see that there is a correlation as we showed earlier. I also can just output this out as a data frame. Now, another thing you can do that's very similar to if you're using Excel, for example, is you can do a correlation, a pivot table. And so in this case, what I do is I take that data frame and I pivot it and I create a team, total millions, and valuation of the team. So I take the attendance, the team name, and the valuation, and I create a plot here using this command PLT subplots, and then I put a title in that says NBA team average attendance versus valuation. And this is just another way of visually looking at the data. And this is, again, really common when you're looking through the data is to visualize it so you can see if you can find some kind of a weird pattern. So, for example, this one looks kind of like a strange pattern, or here we go. We were talking about that earlier. Why do all these teams over here, these are dark, these are lighter, but why is this one 3,000? So why is this, why are the LA Lakers worth so much money? They don't appear to be, they don't appear to have as high of attendance, right? So there's something unusual going on here. And so a next step as well is you can go and use statistical techniques, even before getting into machine learning, to get a feel for what you're ultimately going to do. And so what we can do is we know that the valuation is influenced by the total attendance per year. And so what I can do is I can run a linear regression. And I'm going to use the Python module SMF, and I do a fit on that data set here. And then if I print out the results, we can see that actually the R squared shows that there is something going on. And that's really the way to interpret a linear regression, is if you look at the R squared or the adjusted R squared here, this shows the relationship between the change that's affected by this predictor. So how much is the total attendance driving the valuation of the team? And you can say, roughly about 25% of the valuation is driven by the attendance. So we have something here. We have a signal, and then you can look at the p-value as well. And the p-value, the low, if it's, for example, below 0.05, or lower, that's typically means it's statistically significant. Now with data science, you don't necessarily care as much about these classic statistical techniques because you're more looking for a signal, and you don't necessarily even care about causality. You don't care about why it happened. You're just trying to create a prediction. Let's assume we're maybe betting on a basketball game. We just care about what the end result is. And again, in this case, we can see that there's something going on here. So let's dig a little deeper. Let's plot it out, and you can look at the residual plot. And this shows that these are the plots of what wasn't fit. And you can see that there's an unusual pattern. So this is a small data set. And so this is a little bit of noisy data. And then finally, I can go through here and I can print out, if I was going to make a prediction based on that very crude 25% R squared, what would it look like? And you can see here that the predicted values are here. And then we could compare that, for example, with what the actuals are. And if we print this out, if we look at the predicted values versus the actual values, you can see it's not a great prediction. So in this example here, there's a line where this is our prediction line, but then the actual valuations here, they're kind of all over the place, right? There's actually maybe even a nonlinear pattern, right? Like you could make some kind of a nonlinear pattern. So our initial prediction isn't great, but at least it shows us something. Next, I can actually go through and look at and calculate what the actual error rate as well. And so this is a common thing you do in a data science project is you print out the root mean squared error, and there's those tools are available in the stats module. So this is just really the start. So what can we do to make this model better? What we can do is take that fancy metric ELO, which you would think would be a really good metric to add, which is how good a team is relative to another team. So you would think, again, my assumption would be that we know that the attendance is driving the valuation of a team. How about how good they are? Does that drive the total valuation? So let me add that in, and now I have yet another feature that I can use. And if we go through here and we do a correlation heat map, and we look at this correlation heat map, you can see ELO now pops up. And if I look at the valuation, you can see it's actually pretty low. So it's not actually as predictive as I would have thought. But with machine learning, one thing that's also important to point out is that you can actually take lots of signals that are very low, and if you combine them together, you can actually get a result that you're looking for. So there is something going on, but maybe not as much as the attendance. And so I can print this out as well and look at the correlation, and you can see it's only, in terms of valuation, a 0.06, so pretty low correlation here with how good a team is, which is, again, pretty surprising. You would think that fans would want to go to games where the teams are really good, but what this is saying is that fans actually don't care how good their team is, which may not be surprising to sports fans. Now, if I go through here and I do another analysis, there's another plot I can do, and this just shows me the total attendance, and then I can actually facet it, and I can show the Eastern Conference and Western Conference of the NBA, and you can see that there is a bit of we'll call it a parity problem, where the West Conference actually has a much higher ELO rating, and in fact, the attendance is actually a little bit lower. So it's kind of surprising in a way that the Eastern Conference has better attendance but worse teams, and then the Western Conference has actually better teams and worse attendance. So if we go through here, we can take a look at this, and I can do a group by operation. And so this is very similar to like a group by operation in SQL, and I can actually look at the median performance here. In this case, this is the ELO rating, and I again can tell that the West Coast teams are all a little bit better than the East Coast teams. But then if I go to the attendance, it shows that the attendance actually is a little bit better as well. So actually both are actually there. Now let's go and let's look at a linear regression for this as well. So let's go ahead and see what that would look like. So I run a linear regression where I use ELO to see if I can predict the total attendance. And you can see that it's a very, very low impact. So how good a team is versus how many people show up, there is really a low relationship. So now I'm kind of stuck. So what do? I still haven't figured out why teams are worth what they're worth. I only know 25% of the story. So I might need to start looking at additional data. And so what I do here is I start to grab some housing data. And so I have the county that a team is in here. I have the median home price. I also have the county population. And so let's see if there's something other than basketball, right? We're looking at basketball metrics. Is there maybe a societal issue that could play into what a team is worth? And now we look at this columns here on the data frame. You can see what columns are available. You can see I have the teams, I have the games, the percentage attendance. I have a really large data set now that I've been merging together. And I have these new values, median, home price, and county price in millions. Now let's do a linear regression that actually takes all of those things together and sees, and I can see if I can make a more accurate prediction. So in this case, I take the median home price, I take the total attendance, I take the county population, and I regress and I try to predict the valuation. And look, we've got a dramatically different result. So we can see that actually the county population and the home price are actually more of a driver for why a team is worth what it's worth than actually the attendance itself, or even how good a team is. And so in this case, you can see that the adjusted R squared here, I'm able to tell about 80% of why a team is worth what it's worth by looking at the county population and also the median home price. So that's really the driver for what a team is worth. So now that I've got an idea of what's going on, now I can kind of go down a different road and start using machine learning to further get into the details of my analysis. Let's talk for a second about why you would use unsupervised machine learning versus supervised. So supervised machine learning is a kind of prediction where you already know what the correct answer is. And a good example is if you're trying to predict, let's say, who's going to win next season, you already have last season's data. You have, how many games they won. And so you could use that historical data and you could predict a future value off of it. And that's how how all supervised machine learning works. Unsupervised machine learning is a very different approach. What you're doing is you're using unlabeled data. So you have no idea what the correct answer is, and you're trying to discover hidden patterns and hidden labels. So let me show you a good example of how that would work for a very similar data set. In this case, this is the NBA, and this is a totally different data set from even earlier. And let me shrink it a little bit so I can get it on one screen. So in this case, let me make it a little bit bigger. Here we go. Yeah, this is about right. So in this case, this is a data set that, that's about perfect. So this is a data set that shows a clustered analysis of the NBA. And there's actually 4 different things that I clustered on. So I have rebounds, so over here, I have points over here, and then I have blocks, which are a different dimension. So the more red they are, the more blocks a player has, and then assists show up here, and this is the larger a circle is, the more assists they have. So I'm able to capture 4 different dimensions on this clustered plot. And the higher up you go here, that's the more rebounds you have, and the farther to the right, that's how many points you have. So in this example, I ran unsupervised machine learning, and I created 8 clusters. I think it's 1, 2, 3, 4, 5, 6, 7, 8 clusters. And I didn't tell it what these labels were. It discovered these labels. And what it discovered was there was a cluster right here. And this cluster had players that scored a lot of points. This was Kevin Durant, LeBron James, Carmelo Anthony, Blake Griffin, Kevin Love. And also, if you look at the rebounds, they also have quite a few rebounds, right? They're right in the middle here. And also in terms of blocks, right? They're basically, in the median here, they have a pretty good number of blocks. And if you look at the assists, they also have a pretty large circle. So I could now, as a domain expert in basketball, I could label this. I could label this cluster, and I could say, these are the best players in the NBA. This is several years ago. Now, I also see a different cluster here. And this cluster is very different than this cluster. And what this shows is that these are very red. If you notice, these are purple, these are blue, but this particular cluster stands out from everybody else. And if you look here, they have very high amount of blocks. And also, if you look at the rebounds, look at how high those rebounds are as well. They're actually much higher than, let's say, this cluster or this cluster. And what this is showing me is that if I look at the names of the players, DeAndre Jordan, Tim Duncan, these are elite big men. So these are all players that are, let's say, 6'11", 7 feet tall. They block a lot of shots. They also get a lot of rebounds. And so now as a domain expert, I can label this. And I know that these are all the elite big men. And so I didn't have to go through every single player in the NBA and kind of categorize it. This algorithm figured it out for me. Next, let's look at this cluster. So if you see something's really unique about this cluster as well, look at how large the circles are. And we know that the assists here show how large the circles are. And so I can see that these players are actually really good at making assists. And look, the rebounds are actually relatively low. If there's 4 tiers here, like 300 rebounds per year, you can see that they're at the lower tier. These best players are at a higher tier. These elite big men are higher. So these are actually ball handlers. So these are the point guards of the NBA. You can see Steph Curry has been one of the best players in the NBA for quite some time. Chris Paul as well. And I can label this elite ball handler. So really in a nutshell, this is what unsupervised machine learning does, is it allows you to discover hidden patterns in data. And if a domain expert then sees those hidden patterns, it'll dawn on them that, oh, okay, I know what these are. And then they can label those. So it's a really powerful technique to use when you're stuck and you're trying to do exploratory data analysis and you're trying to figure out the next step to do. And fortunately, in Python, it's very straightforward. So that's what we're going to do next. We're going to get into using some unsupervised machine learning and discover some hidden patterns. So in order to do that, I'll make this a little bit bigger again. In order to do that, we have to first prepare our data for clustering. And this is one of the easiest ways to make a mistake when you're doing machine learning, is to not prepare your data. And there's really 2 steps here. First, I have to make the data frame only have numerical data. So I have to get rid of those other values that are, let's say, text-based values. And so that's what I do here, is I make a subset data frame here, and I put in the total attendance, which is numerical, the ELO, which is how good the team is, the valuation in millions, the median home price. Now, one other thing that's really important is I have to scale the data. And most machine learning algorithms, not all, like linear regression and decision trees, for example, don't require scaling data, but most algorithms do require you to pre-process it. And why do you do this? Is because the features, let's say in this case, the total attendance or ELO or valuation in millions, they all could have different units. So one could be in, let's say, inches, another one could be in miles. And so if you compare things that have different units, you'll dramatically distort your algorithm. And so the way to handle that is we can actually use scikit-learn preprocessing. And there's several different scalars. There's a standard scaler, there's min-max scaler. We're going to use the min-max scaler. And what this min-max scaler does, as you can see here, is it transforms the data so that it's all between a value of 0 and a value of 1. And from here, now I can see that everything is relative. So if I do an apples to apples comparison, now I'm not going to have one value that's going to completely distort things. So once I've done those 2 steps, to step A, numerical, step 2, transform it, now I can do k-means clustering. And k-means is probably the most common form of clustering that is used. And what this does is it allows us to actually find things by creating an arbitrary amount of clusters. Now here I say from scikit-learn cluster import k-means. And then this is the one part that's a little bit tricky, is that how do you decide the number of clusters? And we'll get into that in a second. There's actually a couple techniques that can help you, but it's either going to be you decide it because you're the domain expert, or you use a technique like an elbow plot. So in this case, I'm going to choose 3. I then go through and I fit it. And then once I'm done, I add a new column on my data frame called cluster, and I add that cluster assignment to my data frame. Let's go ahead and do that. And now if I scroll over here, you can see that this cluster shows up right here. So I have this cluster 2. So the first 2 are cluster 2, Chicago Bulls and Dallas Mavericks. Sacramento Kings are cluster 0. So they're totally different clusters. Now, I was talking earlier about this elbow method. There's a library called Yellowbrick that I use quite a bit that has a built-in elbow method visualizer. And if you click it, what happens is I can pass in the k-means clustering data, and I can say, create between 3 to 12 different clusters, and then it'll show you, basically what it would look like, the distortion score. Another way to do this, if you do it by hand, is to actually hand code a elbow plot. In this case, I can say, make a bunch of different clusters and measure how distorted they are. And if I look at this, this is really how you interpret an elbow plot, is if I had one cluster, you can see my distortion is here. It's really high distortion. If I have 10 clusters, I have a very low distortion. So I want to find the elbow, right? So I want to find the spot where does this curve up? And you can see here that it looks like it's 3. And so that's why I chose 3 clusters, is this appears to be the elbow of this elbow plot analysis. So if you're stuck about deciding how many clusters, use an elbow plot. Here's the code to do it. You can just paste in your algorithm and interpret the results. There's another plot you can use as well called a silhouette plot that does something very, very similar. So let's go ahead and run that. So I go through here, I initialize my cluster, and then this is a bunch of boilerplate code that basically plots out a silhouette plot. And from here, you can see that there's a line, which is a silhouette line. And one way to interpret this is that you always want the clusters to be over this line. Ideally, you would like the clusters to be the same size, but with a very small data set like this, you're going to have situations where this cluster is overpowering this other cluster, and there's nothing that you can do about it. But in general, if you have a very large data set, ideally, you would have the silhouette plot sections here all have similar cluster size, and also that they're all over this silhouette. And in this case, we do know that this is actually over the silhouette. So we know that 3 is a pretty good cluster size. You also can get into a more advanced clustering if you'd like, called a hierarchical clustering. And I can compare the two. And again, this is just some boilerplate code. I'll just run this. And so what this does is it shows us that here's the k-means clustering, and here's the hierarchical clustering. And I can see that k-means clustering does a really good job of separating things. And so I can see that there's a distinct cluster here, and there's a distinct cluster here. With this hierarchical cluster technique for this particular data set, it doesn't work as well. And you can see like that it's really hard to divide up these clusters. You'd have to basically do a really strange diagram. So this really isn't a better approach. So for this data set, so k-means clustering, which again is probably the most common form of clustering, is really a good safe bet. Now that I've got that data though, what we can do is we can get in here and actually do a really sophisticated plot. And this might be a little bit hard to read, but you can always, on your own, you have this notebook, download it and maybe put it on a 49-inch monitor and look at it. But basically, I can now in 3 dimensions plot my clusters. And so what's really valuable about doing 3-dimensional plots with clustering is that all of a sudden you'll see something that will make sense once you visualized it that you didn't see before. And what we can see here is that on this axis, this is how good the team is. So the higher up you are, the better you are. And now look, you can see the Golden State Warriors are just staggering above everybody else in the NBA. This was, I think, 2016 to 17. So just dramatically better. Now look at the valuation of the team. This is the axis here. So the farther you go to the right, the more the team's worth. Now, it's not surprising that the Golden State Warriors are one of the most valuable teams, but what is surprising is look at how bad the Los Angeles Lakers are and how bad the New York Knicks are. They're literally the worst teams in the NBA, and they're worth the most money. So there's something very strange going on here. And what we can see here is that this might explain what's happening, is that the median home price, if you look here, the higher you go up this axis, the more the median home price rises. And you can see that LA Lakers and New York Knicks are also just staggeringly higher median home price here. And so what happens is that now that I have these 3 clusters, I could start to really make some conclusions about why they got clustered the way they are. So we could say that the blue cluster these are basically really good teams that are, valued appropriately, right? So these are great teams in the NBA that have an appropriate valuation. And then we have this red cluster, which is we have teams that are very poor teams. So Philadelphia 76ers, before they got a lot of their players, currently they're a really good team, but this is from a few years ago. Orlando Magic, Phoenix Suns, Sacramento Kings, very bad teams and worth very little. So this might be, if you were a billionaire that was looking to buy a team, maybe you would want to look at one of these teams and resurrect it because you get a good deal. It's like going to the dollar store if you're a billionaire. Now, if you go to this section, this cluster, these are actually highly valued teams that are poor performers. And so really this shows the power of how this clustering instantly allows us to do a really interesting analysis. Now, it also opens up really interesting questions. Why is housing so important? So next, as a data scientist, you may decide to completely go on a tangent and start digging into that. So that's what we're going to do here, is we're going to get into that in a second. So finally, I'll just show you a couple of the things that come up as well with unsupervised machine learning. Is there's something called principal component analysis. It doesn't really fit for this model because it's so small, but when you're dealing with highly dimensional data, let's say you have more columns or more features than rows, a principal component analysis can shrink it down so that it performs better with algorithms. And this is just an example of how you could do that. And then another technique as well that you can use is Yellow Brick Road for feature ranking. And so you could install it here if it wasn't installed in your notebook. And then if you run Yellow Brick feature ranking, you can see here that the value of the team here and the total attendance, right? There's a high feature ranking, and also the median home price and the valuation of the team. You can see is actually like that's the best feature, which now explains our model. Now there's a couple other things you could do as well. If you wanted to repackage this model and let's say turn it into a classification model, and a classification model is dealing with things like true or false or red or blue or winning or losing. You could import a classifier, and this is how you would do that. If you wanted to use, instead of the linear regression, you wanted to use a machine learning based regression, you could go through and you could do something like this. I'll let you plug that in on your own. Also, another approach you could use that happens quite a bit is you can also use auto sklearn. And so this is an emerging trend that is very interesting in that you can actually use an algorithm that will programmatically give you a prediction where you don't have to necessarily tune the hyperparameters. And we'll get into that a little bit more at the end. Now, as I mentioned earlier, because as data scientists, a lot of times you'll have an idea, you'll come up with a conclusion, and we came up with something that was really powerful, which is we found out that real estate was a driver for NBA performance. But now that we found that out, why don't we dig deeper and let's really dig into what's happening in real estate. So in this example, I load a library called Plotly, and this allows me inside of Colab Notebook to do real-time interactive visualizations. And so what I'm going to do here is I'm going to again import a lot of libraries here, and then I'm going to pull in a separate data set. Now, I didn't even use this data set earlier, but this data set is from Zillow, and it shows the last 30 years of housing prices. And if I do a description here, you can see that there's a total of 15,000 rows. So there's a lot of data in this data set. Typically, you also have to clean things up. It's almost never that you get a data set and it's exactly the way you want. So for example, I don't know why Zillow did this, but they called the region name, they called the zip code the region name. So I don't know why you want to call it the region name. So I renamed it to the zip code so I understand what it's doing. I also had to clean up the formatting of some columns. That's what I do right there. And now that I've got that data, I can look at the data frame and I can look at, let's say, the median home price of the whole United States over the last several years. Here we can see that in 2017, the median home price was $183,000. Now, if you're in Los Angeles or San Francisco or New York, that is not the median home price. So we've got something going on here. Now what I can do is I can look at several counties in the Bay Area, which is one of the most explosive areas of real estate right now. And I can put those into a data frame. So what I do is I grab the median home price for Marin County, the median home price for San Francisco County, and the median home price for Palo Alto. And I put those all together. Now that those are on data frame, now I'm going to do my interactive data visualization. So let's go through here and load Plotly. And one thing to point out here that's really powerful about Plotly is it fits really well with a data frame, a Pandas data frame. So I use a library called Cufflinks. And what Cufflinks does is it really injects itself inside of a Pandas data frame. So from here, I just have a iPlot method that's available because I imported Cufflinks. And it's really simple to actually do a visualization. I just need to put in a title, and then I title the X column and the Y column. I decide what kind of shape and whether I want to fill plot. Once I run this will take a second. Actually, I think I need to install Cufflinks here, so I'll go ahead and install that. And I can actually just do that right here, which is pretty easy to do. So I'll show you now how to do a real-time installation. So you can do the exclamation point, which runs a shell command, and then I can do a pip install, and then I typically do a -Q, so it quiets the output so that you don't have a bunch of noise in your notebook. And then I can install Cufflinks, and this should work. It should just take a second. Now, if you don't put this, it'll just make like lines and lines and lines and lines of code, and it'll be a little bit irritating to have to look at it. Okay, that looks like it's installed. Let's cross our fingers here. Does this work? And so now what it's doing is it's taking a really large data set. It's like 15,000 columns, and it's basically shrinking it down to this interactive data visualization. And so we can see here we've got Marin County, San Francisco, Palo Alto, and the median in the United States. So now I can look at the sales price here, and I can look at the year. And again, this is the last 30 years. So let's take a look here. If I hover over this, I can see the prices in real time. So this is a really powerful technique to explore the data. And one of the things that we see here is that, let's say in the year 2000, the median home price in the United States was 121,000, and in San Francisco it was much more expensive. It was close to triple, or in Marin County was even higher. Palo Alto was let's say 4 times higher. But if you look at this, it appears there's a very weird trend happening. And what's happening is that even though there was a big housing crash that bottomed out here, right around 2009, you look at the median home price in the United States is really flat. So just in most places, housing is not this exponential growth investment where you're always going to be making tons of money. In the Bay Area, and especially Palo Alto, where they have Facebook, Google, look at 2009, 2010, up until 2017, we have straight exponential growth. And if anyone has studied microbiology or any kind of a science, what happens to exponential growth? Eventually, exponential growth becomes not exponential, right? So there's something very weird happening in San Francisco, in Marin County, and also compared to the median United States, right? The median home price in the United States is not exponentially growing, but something's happening in Palo Alto. And if you look at some of the things that have happened recently, the state of California actually has basically just declared a state of emergency. There's a statewide cap on rent, which is really unusual. There's huge homeless problems. The median rent price in some places in San Francisco, I think in Palo Alto, is between $5,000 and $6,000 for 1 bedroom. So there's something really strange happening in the Bay Area. So now if I go back and I think about the MBA valuation, okay, now maybe that explains why certain regions are so highly valued. It's nothing to do at all with the team. It has to do with the underlying exponential growth or bubble of the real estate. And so that also could be something to take into account if somebody was looking into buying or investing into an MBA team is maybe you don't want to invest in a team where you're basically investing in real estate. Maybe you want to invest in more like a median level team where you're not getting this exponential growth because there's a lot of risk with that. There's no guarantee that's going to continue to grow exponentially. Now, I also can do clustering to further get into this analysis. So let's go ahead and do the same approach here. So I say from scikit-learn, import the scalar. I also drop all the columns that aren't numerical. So I just I drop zip code, right? That's a categorical variable, city, state, metro. And then I go through here and I describe this. And then I go through, I run a scale operation and I do my cluster. Once I've done the cluster, I then add that cluster onto my data frame and actually add in a few little tricks here. So one of the things I do is I add a new column called city, zip code, and appreciation ratio. So now I'm going to use that later in an interactive plot so that when I hover over something, I can see what city it is, what the zip code it is, and how much it's appreciated in price in the last 30 years. So now I go back again to Plotly, and I use a fancier plot this time. So it takes a little bit more code, and it's a three-dimensional plot. And what this plot does is it goes through and it creates a X column here, an X-axis, which is appreciation ratio, a Y, which is the year 1996, a Z, which is the year 2017, the most recent for this data set. And then the text itself, I let it hover, so it's that value that I created. So it's the city, the zip code, the appreciation ratio, and then I also can decide what the color is. In this case, I add another dimension, which is I cluster on color. The clusters become a color. So now if I go through here and I make this interactive 3D visualization, what's really powerful about this is I also can really dig into the data now. So I can zoom out a little bit. I can move this around, and what's powerful is that I instantly see some very weird things. And so one of the things I can see here is that this is weird. Why is this one location popping up here? Why is it totally again, why does it have the highest appreciation, right? So this axis is how many times has it doubled in the last 30 years? And this is Jersey City. So Jersey City 30 years ago, if you bought a home for $140,000, it would now be worth, and this was a couple years ago, this would be worth 1.3 million. So Jersey City, I think, is right next to Manhattan. So maybe the reason that this city went up so much is that it's a commuter city for Manhattan, and Manhattan real estate prices have gone up. Now, another thing that's interesting is if you look at the 2017 prices, is that compared to the Bay Area, this is like a starter home. Like this is nothing compared to the Bay Area. And if you look at the most expensive homes, period, in all of the United States, Beverly Hills 90210, right? Not a surprise, right? There's a whole TV show about Beverly Hills 90210. And it has actually got, in addition to being very expensive in gross terms, in this case, this zip code 90210, if you want to buy a house there, you better have 5.6 million saved away. But it's also has gone up 4 times as well. So you would have made a lot of money 30 years ago buying a house in Beverly Hills. But look what's right below here, Palo Alto. So this also shows that Palo Alto is basically Beverly Hills 90210. So I think this is maybe another surprising thing for tech workers is that how many people would just decide that they're going to be a resident of Beverly Hills? You would expect that if you're like you have a trust fund, or you just sold a company for $100 million, that maybe you would decide you would want to live in Beverly Hills. But this is a very, very wealthy area. But a lot of people have decided to move to the Bay Area, move to Palo Alto, and it's basically 90210. So it's that expensive. And so this is the other thing that's happening is that this, again, if let's say that there's an MBA team that was deciding to move to Palo Alto, you may want to be very, very cautious because the real estate value is appreciated so quickly and so high that there could be catastrophic consequences to moving to that. So really a lot of really fun data you can look here. Now, if you wanted to figure out what was a bargain, what was one of the what was one of the clusters here? Like this is, we'll call this the value cluster, right? This turquoise. This might have been a real bargain area to invest in real estate in the last 30 years. So if you bought a house for $78,000 30 years ago in Philadelphia in zip code 19130, you would have gone up 6.94 times. So 7 times, and now your home would be worth $500,000. So this would have been a great buy. Another one, another Philadelphia zip code. So you can see Philadelphia and Denver were in terms of just a bargain, were incredible places to invest in real estate in the last 30 years. And you got a lot of bang for your buck. So again, these are things that you see only by doing interactive data visualization and doing unsupervised machine learning. So let's dive down a little bit more here and see some other things that I could cluster on and do visualizations. So I have an example of, I can hand code a plot as well. And sometimes this is something you may want to do for executives in your company, is literally just step by step, just put the data into a plot. And what this does is it creates a pretty interesting plot here that shows the endorsements of a player, and I can toggle this on and off. So I could basically turn off, and I could look at only the salary in millions and Twitter favorite count, for example, of these players. And here we can see that there's actually almost the millions in Twitter followers and Steph Curry's salary are basically the same. And so you can see that maybe he's being underpaid here, right? Because he has a pretty incredible social media following. But then if you look at LeBron James here, he's getting 30 million, but Steph Curry at this time was only getting 12 million. So he actually did later get a lot more money. So you can see that this is really a rising star of social media, and he should be getting a lot more money. And if you look at the endorsement, you can see that the endorsement also shows that he's also getting pretty good endorsement revenue. So he's most likely underpaid. Now, a couple other things that we don't have time to go too much more into detail because we're about to run out of time here, but I'll cover some highlights here, and you can get through some of this on your own. Is that hopefully what I showed you is that in the real world, feature engineering, deciding what you want to put into a model is like this. You have some data, and it's not a direct path. It's a winding road. You go back and forth, and you look in one direction, get a dead end, and have to go to another one. So it's full of false starts, frustrating delays, infrastructure problems, laptop problems. For example, your laptop is in production. I think a lot of people in networking know that. And the real world isn't a Kaggle contest. It's a lot messier. And so with feature engineering, one of the things that happens is that this is what you do, is you have your source data and you select and merge it, which is what I showed you. And then I take that raw data and I clean and transform it, and that's what turns into features. You take those features, you then convert them to a model. Those models then give you insight. And really that's the journey that we just went through. Another thing to point out as well about machine learning is that ML code is really the smallest aspect of what's happening in a machine learning project. And a lot of times there are people that are really obsessed with doing machine learning, and that's great. It's a fun thing to know how to do, but it's a lot like saying, you're the network cable specialist, and what you want to do is you want to focus on cutting cables and putting them into servers. Well, there is certainly an aspect of that in building out a data center, but that's a component of what you're doing. You also have to rack things. You have to buy the storage. You have to understand how to configure the network switch. There's lots of things you're doing other than just putting the cables in. So it's same with machine learning code here. You can see that there's configuration, data collection, feature extraction, data verification, machine resource management, analysis tools, serving infrastructure, monitoring. And this is really a real world view of what happens with data science. So in terms of some takeaways here, one of the things to point out is that machine learning code is a lot like the cherry on a sundae, and everything else is the sundae, right? You got the glass, you got the ice cream, you got the hot fudge, the whipped cream, and then the final piece is you put the machine learning code in there. And so, 5% of the code in a machine learning system is the ML code, and probably 95% of it is the glue code. And Here's another diagram that's kind of interesting is if you look at data science, this is really like a research position, but a machine learning engineer really handles operationalizing machine learning and optimizing machine learning. And a data engineer handles advanced programming and distributed systems. So because we're about where I wanted to end at, I'm going to just let you see a few other sections here that you may want to follow up on your own. If you want to get into further diving into this model, you can look at feature engineering in practice, scaling data. You can look at bias. There's some case studies. There's also some AutoML code in there. So there's a lot of other things you can follow up on your own on, but this should be a good overview of what it would take to do data science. So from here, I think I can go through and maybe answer a few questions if there's any Q&A, and I could just hang out for a little bit if there's any more questions. All right, well, thank you very much. I appreciated everybody that showed up, and I will look forward to seeing you soon in the future.